Hello, hello. Am I audible, guys? Hello, 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 hello. I'm Suvrat and today we'll be discussing starters 201 CodeChef. So let's start with the discussion. So problem A, mixing liquids. Chef is now making orange juice. He has A units of orange syrup and B units of water. To make orange juice, chef must mix the orange syrup and the water in exactly a 1:2 ratio, otherwise the recipe is spoiled. Further, chef can only use integer amounts of liquid because his measuring cylinder cannot accurately measure fractional quantities. Chef wants to make as much orange juice as possible. How much will he be able to make? The total quantity of orange juice is the sum of units of orange syrup and water. And each test case has A and B. There are 100 test cases and A and B are till 100. So problem A. Basically the problem says that we have A units of orange syrup and B units of water, and we need to mix them in a 1:2 ratio where one part of orange syrup corresponds to 2 parts of water. So basically we need to find out what is the maximum amount of juice that we can make. So let's see the test cases. 1, 5. So basically, since we have only one unit of orange juice, we can mix it with 2 units of water to get 3 units of orange juice. And since there aren't any more units of orange syrup left, so 3 would be the maximum orange juice that we can make. Next test case is 5, 5. Here in this case, we can take a maximum of 2 units of orange syrup because taking 3 would require 6. Taking 3 would require 6 units of water. So we cannot do that because we only have 5 units of water. So we will take 2 units of orange syrup with 4 units of water. This will give us 6 units of orange juice. So 6 is the answer. Then 10, 1. So here we cannot choose even a single unit of orange syrup because there is only 1 unit of orange. There is only 1 unit of water, and for just 1 unit of orange syrup, we require 2 units of water. So since we only have 1 unit of water, we won't be able to make any orange juice here. So answer for this would be 0. So let's solve the question like this. Basically, we have B units of water, right? So we can take a maximum of floor of B by 2 units of water, units of orange syrup. Basically, let's say we have 7 units of water, then B by 2 floor would be 7 by 2, which is 3. So we cannot take more than 3 units of orange syrup because 3 units of orange syrup takes up 6 units of water. When we try to increase 3 to 4, then we take up 8 units of water, but we only have a but we only have 7 units of water. So B by 2 is the maximum units of orange syrup that you can take for B units of water. So basically B by 2 is the maximum units of orange juice, orange syrup we can take if we have B units of water. So this was the observation, and basically since we need to maximize the orange juice, so we would be taking maximum possible orange syrup, which would be minimum of B by 2 comma A. This would give us the maximum possible syrup that we can use. Basically, if A is more than B by 2, then we can only select a maximum of B by 2 units, and if A is less than B by 2, then we will select A units, because we can only select a maximum of B by 2 units. So minimum of B by 2 comma A is the maximum amount of orange syrup that we can select. So our answer would be, since we are mixing in 1:2 ratio, so for each part of orange juice there are 2 parts of water. So overall quantity of juice would be 3 into minimum of B by 2 comma A. Since this is equal to the number of parts of syrup, and there are 2 parts of water for each part of syrup, so total 3 parts. So total 3 into this would give us the final answer. So I'll show you guys the code for this. Basically, I see in AB, and then I divide B by 2. Then x is the minimum of A comma B. Here B is B by 2 actually, because I have divided B by 2, and then 3 into x would be the answer. So that was the solution for problem A. If anyone has any doubts, they can ask. Okay, so let's move on to the next problem. So the next problem is mark points. There are n equispaced points numbered 1, 2 till n. Initially, all points are unmarked. In one operation, you can choose x such that x is between 1 and n, and then mark points x minus 1, x and x plus 1. If any of them were already marked, they do not get affected. Finally, you will make a binary string S where Si equal to 1 if and only if you have marked point I, and otherwise Si equal to 0. Now you forgot what operations you did and you have a binary string S with you. You want to check if it is possible to obtain S by doing some of the above operations of marking points. Print yes if it is possible to obtain S and no otherwise. So basically problem B. We are given a binary string S which is initially all zeros. A string S was initially all zeros, and then we can perform operations on it. In one operation, what we can do is mark x minus 1 and x plus 1th indexes as 1. We can do this operation any number of times, and let's just call this S1, and we need to tell if S1 can be converted into the string S that is given in the question. So basically let's try the test cases. So first test case is 0, 0, 0. Here we don't need to perform any operations, and because the initial string is the same as the string, so yes, for 1111, what we can do is initially we add 0000, then we can select these three and perform the operation, and then we can select these three and perform the operation. So we will get this. So answer for this is also yes. 00101. So 00101. So there is no way that we can just mark a single element as 1. So answer for this is no. And the observation is that we cannot mark a single index as 1, since in each operation we mark 3 indices as 1. So there can never be a single one with zeros on both sides in the string. So no. Then the next test case is 0110 111. So again in this test case, initially we will have this string. Then what we can do is perform operation on these three to get this. But then we will not be able to get these two, since there has to be a minimum of 3, because if I perform operation on any of this index, they would give me minimum of 3 ones. So again, there cannot be continuous ones with size less than 3. The next test case is 1110 Here we can perform on this index, then this index, and then this index, and then we'll get this string. So yes. And then 0011 again, there cannot be groups of 1 with less than 3 ones. So again no, and again 2 ones cannot be made. So again no. So basically the key observation here is since in each operation we mark 3 consecutive elements as 1, so we can never in our array, in our string, have 010 or 0110. Basically, all groups of ones must have size greater than 3. And it can have any size greater than equal to 3. I can prove that easily. Let's say that we had some binary string. Then let's say we need to mark 5 of these as 1s. So what we can do is select this index and then perform this operation. Then next we can select this index and perform this operation. Then we can perform this operation. So we can perform these operations to create any groups of 1 with whatever length we want, but we can never create with size less than 2. Basically, we can never create 1 1 or 1. We can create 1 1 1 or 1 1 1 1 or 1 1 1 1 1. We can create these, but we cannot create of size 2 or of size 1. So basically, to solve this question, we need to check if in the string we have these or not. So if we have 1 1 or 1 in the string, then no, else yes. So to check for this, we can basically count the length of all the groups of ones, and to do that we can perform a simple loop for I equal to 0 till I till n and I plus plus, and basically we can maintain a variable curve which gives us the length of the current group of ones. So if the current element is 0, then basically we set current as 0, else we just increase current. And here we can check if current was, wait just a second, here we can check if current was between 1 and 2, then that means the current group was between length 1 and 2, and we can just simply see out no. And since v of I is 0, we can again set our current to 0, else we can increase our current. We can perform a little dry run for this algorithm. Basically, let's just take some string 11001110110111. Now we are iterating over this string and our current variable. So first element is 1, initially current is 0, first element is 1, so current becomes 1, then next element is 1, so current becomes 2, then next element is 0, so current becomes 0, and we know that we have a group of 2. Then again next element is 0, so our current remains 0, then our current becomes 1, current becomes 2, current becomes 3, then the next element is 0, so current becomes 0, and we know that there is a group of 3. The next element is 1, so current becomes 1, current becomes 2, the next element is 0, so again current becomes 0, and we know that we have a group of 2. So group of 2 was this, group of 3 was this, group of 2 was this, then again 1, 2, 3, and then we'll know we have a group of 3. So we can check like this, if there was any group of group with elements less than 3, then that would tell us whether the answer is no or yes. So this can be done in O of n, since we are iterating over the string only once. So I'll show you guys the code for this. Basically streeness and boolean check would in the end tell me that did we find any groups of length 1 or 2. So current is the variable that tells us the length of current group. So if Si is 1, then I increase the length of current group, else if Si was 0, then that means the current group has ended, and I check whether the current group had elements had size between 1 and 2, and if it had size between 1 and 2, then I set check as false, and for the next group I again set my current as 0. And in the end, for the last group, it may not enter into this else loop, so I have to check it outside the loop and mark check as false. So if checked, then I see out yes, that means there was no group of length 1 or 2, else see out no. So did you guys understand this solution? If anyone has any doubts, they can ask. For next question, please create the matrix for 0, 1, 1, 0. Okay. Okay, so let's move on to the next question. So huge grid, easy version. This is the easy version of the problem. Here your task is to find the minimum possible path sum. Given a binary sequence A of length n, we can construct an n into n matrix B as follows. Bij is basically sum from Ai till Aj. Otherwise and Bij is equal to Bji. So if I is less than j, then Bij is sum. Otherwise Bij is Bji. So define a path from 1 comma 1 to n comma n as a sequence of pairs. This where okay, whatever, and the path sum is defined as sum of bij's over the path. Then your task is to find the minimum possible path sum, and n is given as 1e6. So expected time complexity would be O of n. So problem C. Basically, we are given a what is that? Okay. So we are given a sequence A of length n, and we are constructing from a matrix B, where B of ij is equal to sum of ax from x equal to I till j when I is less than j, else bji is bij. And in this matrix B, we would have 1, 2, 3. We have values at each cells, which we get from this formula, and then we need to go from this cell to this cell, and we need to find a path with the least cost. Path could be anything like this. So find path from 1 comma 1 to n comma n with least cost. So let me One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. So this let me index it. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So here it will have the sum from 1 to 1. Here it will have the sum from 1 to 2, 1 to 3, then 1 to 4, then 1 to 5, 1 to 6, and so on. Here it will have from 1 to 2, and since it is symmetric, 1 to 3, 1 to 4, 1 to 5, 1 to 6. Here 2 to 2, so on. And we need to go from here to here, and we need to find the path sum, right? So initially, starting from this index, I can go either here or here, right? So let me draw another one beside this. So basically, I'll start from here, and I can go either here or here. Now, since this is a symmetric matrix, these elements would be same, right? Because Bij is equal to Bji. So basically, I would first add this in my answer, and then I can move on to here or here. But since it is symmetric, both of them have same cost. So I can basically go here, and I would have gotten the same cost as this. So let's just move on to this cell for now. Then I could have moved down, or I could have moved here. And if in the second step from here I had gone here, then again the corresponding symmetric choices would have been moving here or here. Here or here. So basically, since this is a symmetric matrix, we can continue this. From here, I would have choices this, and from here I would have choices this, and the corresponding choices we would have would be this. So basically, since it is a symmetric matrix, we can only stay in the above right half and get the answer. Basically these. Since let's say I am at some point, I had chosen this path and I've come across this cell. So now basically going to this cell or going to this cell would be having the same answer. I would get the same answer from this cell as I would get from this cell, because these both cells have same value because it is a symmetric matrix, and again they would have similar choices of moving here or moving here. So basically I can just use the upper half and solve the question. So let's try to figure out what kind of operations. Let's first solve the test cases now. 0 1 1. So let's also in chat someone asked to zero one one zero. Okay, we'll make for that after 0 1 1. So let's first make for 0 1 1. So this would be 0, this would be 1, and this would be 2. Then since it is symmetric, 1 2, this would be 1, this would be 2, since it is symmetric, 2 and 1. So basically, since now I have to find the minimum cost of going from here to here, I can take this path. Yeah, I don't think there is more optimal answer than this. Yep, so I can take this path, and the answer for this would be 0 plus 1 plus 2 plus 1, which is 5, which is 4. 0 plus 1 plus 1 plus 2 plus 1 is just plus 1 plus 2 plus 1, which is 5. So yep, the answer for 0 1 1 is 5. Let's draw for how to find upper matrix and lower matrix. Basically, this index is the sum from 1 to 1. This index is sum from 1 to 2. This index is sum from 1 to 3. Basically, sum from 1 to 3 would be 0 plus 1 plus 1, which is 2. 1 to 2 would be 0 plus 1, which is 1. 1 to 1 would be just 0. And this index is given as from 2 to 2. So just 1, 2 to 3, 1 plus 1, 2, then 3 to 3, 1. That's how we can find the upper and lower matrix. You cannot actually calculate this matrix for the question, because that would require n square complexity, since the matrix would have size of n square. So you won't be able to calculate in the question, but let's just do for solving the test cases. Now we'll do for 0 1 1 0. 0 1 1 0. So this would be 0 1 2 2, then 1 2 2, then 1 2 2, then 2 2, then 1 0, and 0, then 1. So again, in this case, the optimal would be, I think, this only. So 0 plus 1 plus 1 plus 2 plus 1 plus 0 plus 1. So 1, 2, 3, 4, 5, 6. So 6 would be the answer for this test case. So let's try and understand what's going on. Let's say we are on some square I comma j. So this would have the sum from ith index till jth index, right? This let's assume this is our array. This is the ith and jth index. So this would have this sum. Now if we from this cell go to the next, which would be I comma j plus 1, and the down one would be I plus 1 comma j. So we either shift this, we either add this sum or this sum, right? So we can either choose to go to this cell or we can choose to go to this cell. Now also basically, so it is our obvious choice would be always to select this cell, right? Because this cell would always have a value less than this cell, since this cell contains all the elements from this cell and some more. So our obvious choice would be to always select this cell. So that would mean that we would always move downwards, right? But basically this cell is only valid for cells that actually have a downward cell, because for example for this is from 1 to 1, but this is from 1 to 2. Basically due to symmetricity, these two cells become the same. So in this case we'll just move right and it would remain the same, since we cannot go downwards, since we proved that in a symmetric matrix we would always get our answer from the above triangular matrix. So from 0 we can only go rightwards. Now from rightwards we have a choice to go either right or down. So since we proved that down operations are always better, so we'll go down, and then again we cannot move down, so we'll go right, then we'll go down, then we'll go right, and then we'll go down. So basically this will be the most optimal solution for any binary string. So basically our answer would be just summing 1 2 1 1, then 1 2, then 2 2, then 2 3, then 3 3, and so on, like this. Basically following this path would give us the answer. So did you guys understand that, or you guys have some doubts? I'll explain the code and how to code this and show my code, but just once tell me if you guys understand this or not. I think the 4 4 is 0 instead of 3 4 and 4 3, as they are ones. Oh sorry, 4 4 is zeros. Yep, 4 4 is 0 and this is 1. Sorry, my bad. So that would basically this would be 1 and this would be 0. If I travel to lower triangular matrix, what you can do is basically, let's say that, okay, let me explain this once more. Let's say that you are here and let's say that you travel to the lower triangular matrix, right? So let me just denote some path like this. Now basically this path would be the same as this path, since rest of all the rest from here all the elements are same and these two are same. So basically we'll always have a corresponding mirror image path in the upper triangular matrix for the nodes that you visit in lower triangular matrix. Let me take some other path and explain again. Let me take some other path for, let me take a bigger matrix actually. Okay, so let's say that I have gone from here to here to here, 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 then again here, then here, 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 and again here, and here, 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 and here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8. Let me just, sorry. 1, 2, 3, 4, 5, 6. Okay, so let's just take some path like this, right? And our lower triangular matrix is this one. No need to draw that. Okay, so basically what we could have done is we could have moved symmetrically in the upper triangular matrix, then we could have come down, then again we could have symmetrically moved, then we could have come down, then again we could have symmetrically moved, and then we could have come down. So basically for all the path that we take in lower triangular matrix, we will just take the symmetrical path in upper triangular matrix. And what if we had maybe, let's say that we went into the upper triangular matrix. If we had chosen some path like this, so basically the corresponding would be we could have done this, and then just followed the same path. And then as soon as it went into the lower triangular matrix, we could have just taken the symmetrical path. This is, yeah. So that way we can always, even if we go into the lower triangular matrix, we will always have a path that gives the same sum using just the upper triangular matrix. So did you guys understand why only the upper triangular matrix would always give the answer? Applying dp after making, you cannot make the full matrix because it would be n square. So basically now what we have proved is we can always just travel in the upper right matrix and get the answer. So what we can do is we can always we need to only use this much matrix, right? I always 1, 2, 3, 4, 5, 6. So basically we only need to use this much matrix, and we just now saw that if I comma jth cell had this much subarray, then towards the right I comma j plus 1 would have this subarray, and towards the bottom I plus 1 comma j would have this subarray. So choosing the I plus 1 comma j whenever we can would be the optimal choice, because it obviously has a lower sum than I comma j plus 1. So we'll move down whenever we can. So basically we'll get this path as the most optimal. So we just need to compute the sum of this path, and that would give us the answer. Two into first plus last element works plus 3 into sum of remaining elements. Basically that is working because these two cells would add the first element twice and these two cells would add the last element twice, and rest of the elements would be added 3 times. Basically the second element would be added by this and this. So similarly the third would be added by this and this. Fourth would be added by this. Fifth this, sixth this. So that is why this will work. So the answer for this question would basically be the sum of 1 comma 1 plus 1 comma 2 plus 2 comma 2 plus 2 comma 3, then plus 3 comma 3 plus 3 comma 4, then 4 comma 4, and so on, which is nothing but in a binary string. Let's say this is our string. Basically first we add this element, then we add this element, then we add this, then we add this. Basically let me just put some values. So 1 1 would be just 1, then 1 comma 2 would be 1 0, then simply 0, then 0 1, then simply 1, then 1 0, and so on you can do. Basically first you just need to, for all I equal to 0 to n, basically answer plus equal to b of I, and answer plus equal to b of I plus b of I plus 1. Basically that what this will do is first add 1 to the answer, then add 1 comma 0 to the answer. So 1 is 1 comma 1 and 1 plus 0 is 1 comma 2. Then I would add 0 to my answer and then I would add 0 plus 1 to my answer. So 0 is 2 comma 2, then 2 comma 3, and then 1 1 0 1 1 0. So that way we'll solve the question, and we would not execute this operation for if I plus 1 is greater than equal to. So I plus 1 must be less than. So we need to only iterate over the array once, so the time complexity would be O of n. So the code for this question, basically I am creating this vector v. If c is 1, then vi is 1. If c is 0, then vi is 0. And then for answer, I would just add vi, and then I would add vi plus 1. And I won't perform this addition if I plus 1 is out of bounds, and then I see out the answer. So is the C problem clear for everyone? If someone has any doubts, they can ask. How do you guys visualize this or think about this? Basically, there's a lot of problems where this kind of symmetric matrix, you can just replicate the same paths from lower triangular to the upper triangular matrix. So that is basically something you get from experience. And the next observation, this was basically just visualizing what the operations are actually doing. So when you try to visualize what the operation was doing, so you'll get to know why doing this operation would always be better. So that way, it's about practice. The more you practice, the more you will have clever ideas. How to get better at visualizing? Always try to make diagrams while solving questions, so that way you will start to do that unconsciously while reading a question. Since values are given to be positive, just start going through the path where you are adding these numbers. Okay, so basic. Let's move on to the next question. Just a second. I'll be back in a minute, guys. I need to use the washroom. Okay. So next problem is compare and connect. There is a multiset S containing n plus m strings, n of which are less than and m of which are greater than and less than. For two strings S and T, f s comma t is defined as if s is smaller than t in lexicographical order, then f s comma t is s plus uh, uh, s plus less than t, and if s is equal to t in lexicographical order, then s plus equal to t. If s is larger than s plus greater than t. So you need to perform n plus m minus 1 operations. Each time choose two strings s and t in s. Insert f s comma t to s and erase s from t and s. Finally, only one string remains in s. Find the lexicographically smallest possible string. So in this context, this is the smallest having ASCII value 60, and this is the second smallest having ASCII value 61, and this is the largest having ASCII value 62. And n comma m is given as 2v5. So and its expected time complexity would be O of n, O of m, or O of n log n something. So problem D. Basically, in this problem, we have n these symbols and m these symbols. And what we can do in each operation, choose two strings from the set and remove those two and add. Basically, let's say I have chosen the strings A and B, so I'll add this string if A is less than B lexicographically, and if I add this string in the set if A is greater than B. I'll explain this more clearly through test cases. So let's just check out test cases. So 0 2, 0 2. That means initially the set has these two strings, and then since we need to perform operation and there are only two strings, so we can only perform this operation. So we will remove these two strings, and since they are both equal, we'll add this string in the set. So this would be the answer, since there is only one possible final string. So this would be the most lexicographically smallest. For the next test case, 2, 3, 2, 3, the set would have this and 3 of these. So basically, initially what we can do is first of all, since we need to find the lexicographically smallest string, right? So what we need to do is try to maximize the number of these in the front of the string. So we need to find some strategy that maximizes the number of these symbols in the in front of the string, so that we get the lexicographically smallest string possible. So let's second. So there's like 3 different operations that we can do. We can either select these 2, or we can either select these 2, or we can either select these 2. So let's try and select all of them and look what happens. So if we select these 2, we'll get a string this. If we select these 2, we'll get this string, and if we select these 2, we'll get this string. So obviously, since we are trying to maximize the number of this in the front of the string, so this would be a very good choice. So let's for now do this operation and move on and see what happens. So basically the set would now have this string, and since we used one of these, we'll only have this left. So now there is a very easy observation now that basically this is smaller than all the strings except this. So basically this would be smaller than all the strings except this. So I can do operation on this and any other string to get this and then that string, where a is not equal to this. So what I can do is after the first operation I have gotten this string, right? And since I need to maximize the number of this, so what I can do is I'll use each one of these that I have in my set and do the operation with this and this. So what will happen when I do the operation on this and this? I'll get this string, which is basically maximizing the number of these symbols in the front. So now after this operation, I would have these things in my set. Set this string and then this string. 2 of these, right? Yep. So now basically what we can do is we won't apply the operation on this and this basically in this order. We will never do this f of this comma this, because what doing this operation would put this in the front. So doing this operation is not preferable. So we would always do these operations, comma this. So what this will do is basically, since this string would be larger than this string, since it has this in the beginning, so we will get this string. Or instead of this, what we could have done, and if we again repeat the same process for next bracket, we would get this final answer. Or what we could have done is we could have applied the operation on this and then we could have applied the operation on this. So let's check out that path as well. So basically we would get this and this, and now obviously we will never do this operation, because doing this operation would place this in the front, which we don't want. So we will do this operation, which will give us this string. So basically first we were getting this string and now we have gotten this string, which is bad because first we had this and this. Now we again have this, but we have an equal to in between where we could have gotten this one. So doing this is not preferable, and we would be performing this operation to get the best string possible. So basically we have found an approach. What we can do is select one this and one this in the beginning initially and perform operation on those to get this string, and then for every this we can do f of this comma this, and after we have done these for every this what we can do is f of this comma this. So this would result in this and this would result in, so basically each these type of brackets would add this in our answer, and each this type of bracket would insert this at the beginning of our answer. So what we can do is this plus m minus 1 into this string and plus n minus 1 into this string. Basically, since we have used one of both initially to get this string, we will only have m minus 1 and n minus 1 left, and for all of them we can perform the same operations. We can add two of these in the beginning and we can add this in the end. So this would be the approach, and now we have some special cases of if n equal to 0. So that means we only have these in the array, in the set. So basically initially we would have to pick these two and perform the operation, so we will get this, and then what we can do is since this is greater than all the angle brackets, so we can do this. We can perform f of this comma this. Now I'll be violating my rule of never applying this in the beginning. I said that above because we had in our string we had this in the beginning. So applying adding this at the front would be bad because we need to get lexicographically least. But now applying this at the front would be beneficial because we would be adding this. So at first when we had equal to at the second position, now we will have a less than sign at the second position, which is better than equal to. So for all the greater than signs we can add this in the beginning. So again for this test case we would get our answer as this and m minus 2 into this plus this. So this would be for n equal to 0, and if m was 0 then that means we only had these. So initially we would have to pick these, and now since this is smaller than all strings except this, we can repeatedly perform this operation and we would get basically n minus 2 into this sign plus this. So this would be the answer in this case. So each of the three cases we would only require O of n plus m complexity to generate the final string. So O of n plus m would be the required time complexity. I'll show you guys the code. The case when n was 0, basically this was the first operation, and then I subtract m by 2, and then rest for all the m's I push back this on the string. in the front of the string. So basically I see out f plus answer, and then again when m was 0, then I would initially have this string, and then I would subtract n by 2, and then for all the remaining signs I would add this in the front, 2 of these. So this would be f plus answer. And then when both n and m are positive, then I can perform n minus 1, m minus 1, and initially I would get this string. Then for all the m, I can add this in the back, and for all the n, I can add this in the front. So f plus answer plus b. So that was the code for question number 4. Did you guys understand this solution? If you guys have any doubt, you can ask. We'll be discussing till delete maximum. I'll be discussing the next 2 problems as well. I solved 6 in diff 2. Okay, so can you explain how string is lexicographically smaller than string this? Basically, they are both. Let me just write that. Can you explain how string this is lexicographically smaller than string this? This is not lexicographically smaller. This is the lexicographically smaller string. Lexicographically smaller is A. Basically, initially we have to do this operation because we don't have any other choice. Only then we can start adding this in the front. But first we have to do this. You cannot create that string. You cannot create this string. This string is impossible to create because initially you would have to do this operation. No, I'll not be I won't be discussing hard version of FuseGrid. I was not able to solve that. Is that clear now? How would you get the string B? How would you get that string B? You can never form this string. This can never be formed. Right? Okay. So let's move on to the next question now. So permutation cost sum. You are given a permutation P of length n. Assume you can perform 2 types of operations. Modify Pi to any number at a cost of A, and then swap Pi and Pj at a cost of B. We define f of Pa, B as the minimum cost to make the permutation satisfy Pi equal to I for all I. Your task is to calculate sum of f Pi, j. Since the answer may be large, you need to output it modulo something. So n is given till 2e5. So sum of our n overall test cases does not exceed 2e5. So expected time complexity would be 2e5, O of n only. O of n or O of n log n. Or actually O of n square root n also. So problem, which is, this is 5th problem. Problem E. So basically what we are having two types of operations. Modify pi to any number x. This has a cost equal to a, and other operation is swap pi and pj, and the cost of this operation is b. And basically f of p comma a comma b is minimum cost required to convert a to 1 2 3 n to this array. Sorry, not a, p. Convert the permutation p to this permutation, and minimum cost required to convert that is f of a p a comma b, where a and b are this. And what we need to find is sum of a equal to 1 to n, b equal to 1 to n, f of p comma a comma b, and p we are given in the test case. So let's just first try to focus on finding out what is f a comma b, f p a comma b. So f of p a b. Let's take a test case. Let's take the I think we can take the last test case. We should take 1376245. 1376245. So let's just focus on solving this problem using just swaps. So this is a very well-known problem of basically sorting a permutation using swaps, using minimum number of swaps. So this is like a very famous problem. It comes in a lot of questions in contests. So I'll tell you how to solve this problem. So basically what we can do is 1376245, right? 1376245. So 1 is in its correct position, but 3 is in its wrong position. 3 has to be here, and then 7 has to be here, and then 5 has to be here, and then let me just do it like this. 3 has to be here, 7 has to be here, 5 has to be here, and then 2 has to be here. So basically we have gotten a cycle going on, cycle of these numbers, and then again 6 has to be here and 4 has to be here. So basically the array would always be divided into cycles like these. So how do we sort this using minimum number of swaps? What we can do is let me write that again. 1 3 7 6 2 4 5. So 3 7 2 and 5 we know that are in a cycle, right? So what we can do is swap 3 and 7. So 7 will come here and 3 will come here. We have done one swap, and then now 7 has to go to 5. So 7 will come here and 5 will go there. So another swap, and then 5 will go here and 2 will come here. So now since they were in a cycle, so let's assume that another plus 1. So now we see that all 2, 3, 5 and 7 are in their correct positions in just 3 swaps. So basically in a cycle of x elements, if I swap out the if I swap out x minus 1 elements to their correct position, automatically the last element would be in its correct position, because just a second, last element would be in its correct position. Basically, since I have adjusted x minus 1 elements to be in their correct position, so the last position must correspond to the xth element. So as we saw in this case, what we did was 1376245, right? 1376245. 3, 7, 2 and 5 are in a cycle. So what I did was first place 3 in its correct position, then I place 7 in its correct position, and then I place 5 in its correct position. So 2 automatically comes in its correct position. 2 is automatically in its correct position if I am moving the other x minus 1 elements to the correct position. So basically, and similarly for 6 and 4, if I move 6 to its correct position, 4 will automatically be in its correct position. So for a cycle of x elements, I need to perform x minus 1 into b, x minus 1 b type operations to sort it. Basically, we are doing it in the, we are actually sorting that cycle to minimize the number of operations, because this saves us one operation. For each cycle, it saves us one operation. So the solution for this problem is actually n minus number of cycle, this problem basically. This problem, sorting a permutation using minimum number of steps, the answer to this is n minus number of cycles. Because for each cycle, we require one less step. So here we have 3 cycles. One has a self cycle, and then 3, 7, 2, 5, and then 4, 6. So 3 cycles. So we would require 1, 2, 3, 4, 5, 6, 7 minus 3 equal to 4 operations. So this was the first observation. This, we know this now. Right. So now basically the answer of a equal to 1 to n, b equal to 1 to n, f of p comma a comma b is same as for all cycles a equal to 1 to n, b equal to 1 to n, f of c comma a comma b, where c is the cycle for all cycles c. So basically, we can individually calculate for each cycle and then sum that for all the cycles, and that would be the answer. So now let's focus on calculating this f of c comma a comma b. So let me again choose that cycle that we used above, 3, 7, 2, 4, 2, 5. So 3, 7, 2, 5. So 3 has to go here, 7 wants to go here, 5 wants to come here, and 2 wants to go there. So this is our cycle, right? So we have one solution for this cycle that we can do in 3 into b cost. Since we know that we can perform x minus 1 operations and x minus 1 b type operations, and that is one way we can solve this, right? Another way that we know of would be 4 into a cost. What we can do is basically change this 3 to 2, then 5, then 3, sorry, then 7, then 5, then 7. basically we can change each element to the correct element. So either we can do this or we can do this, or what we can do is we can do a mix of both. So let's analyze this case as well, mix of both, where we would be performing some B operations and then some A operations. So before moving on, there is one observation. We would always perform swaps before A operations. Why so? Why can we do this? Is basically if we are performing the A operation before performing a swap, then what we can do is just perform that A operation after the swap, and that would change nothing. Basically, let's say I have these numbers 3, 5, and I perform the change operation and transform this to 3, 6. I transform 5 to 6, and then I perform the swap operation and it becomes 6, 3. So what I could have done is I could have first performed the swap operation, and then simply I could have changed the values. So basically I can perform the swap operations, all the swap operations first, and then I can perform the change operations, since they are kind of individual, kind of independent. Basically, yeah, they are kind of independent. And also there is no point in applying two change operations on the same index, or actually the same number, basically, through the swaps. So yeah, that is very obvious. So we would always perform swaps before A operations. So let's try and apply to this cycle the mixture of both. So 3725, right? 3725. 3 has to go here, 7 has to go here, 5 has to come here, and 2 has to go. So let's swap 3 and 7. So that would give us 7, and this would give us 3. Now what happened is our cycle changed from this to this. 10 wants to go here, 5 wants to come here, and 2 wants to go there. So basically, now if we want to perform the A operations, we would need to perform 3 A operations. So another solution that we got was 3 A operations plus 1 B operation. And now let's say that we would have continued performing the B operation and perform another B operation here. So let's say we also, let me rewrite it, 7, 3, 2, 5, and then 7 wants to go here, 5. So let's move 7 to its correct position. So 5 will come here and 7 will go there. So now the new cycle would be this. So we would require two B operations, and we can now solve this cycle with 2 A operations. And if we perform another B operation, then we will obviously be back to this thing, 3B. So now basically my point is, just a second. My point is that we would never have to perform any other operation than these. We would only perform one of these, because when we try to perform mix of both, what happened was basically 1B was reduced and 2A was increased, and then further 1B was reduced, and then only 1A was increased. So basically, let's say we have some XBs and X plus 1 A's. Let me just use some value. Let's say there is a cycle of 6 length cycle. So if we try to solve it with just using B's, then we would require 5 B's, or we could have solved using A's and we would require 6 A's. when we try to use a mixture of both, what will happen is basically 4b plus 2a and then 3b plus 3a and then 2b plus 2a and then 1b plus 5a and yeah. So these would be the mixture of operations that we can perform. So why performing these is a waste? Basically because let's assume two cases. One case is if b is less than a. So if b is less than a, then obviously 5b would be always the most optimal, because b is less than a, so 4b plus 2a, so 2a would be greater than 2b, so 4b plus 2a would be greater than 6b, and we already have a solution with just 5b. So all of these would all be more than 5b, and 6a is also obviously more than 5b. So if b is less than a, 5b would be the most optimal answer. And if b is greater than a, then 6a would be the most optimal answer, because obviously we would just keep on reducing the number of b's till we can. Basically, if b is greater than a, then either 5b or 6a would be answer. Any one of these could never be the answer, because here we are just subtracting minus b and adding 1a. So this would always be net negative only, right? Because b is greater than a, so subtracting b and adding a is basically reducing. So we are reducing from here to here, we are reducing from here to here, we are reducing from here to here, we are reducing from here to here. So basically 6a is less than all of these. 6a is less than all of these. So these can never be the answer. If b is less than a, they cannot be the answer. If b is greater than a, again they cannot be the answer. So my point is, for a cycle, we will either perform x minus 1 into b or x into a. So for a cycle of x elements, we will either perform x minus 1 into b or x into a cost. So basically now our function would look like this for all the cycles. A equal to 1 to n, b equal to 1 to n, and minimum of x minus 1 into b comma x into a. So now let's try to solve this equation. So basically let's try to fix the a and solve this summations. Basically this summation, let's try to solve minimum of x minus 1b comma xa. So this would be nothing but, let's now find for what b's this is the lesser value. So let's find the cases where x minus 1b is less than equal to x into a. So b less than equal to xa upon x minus 1. So basically for b equal to 1 till xa upon x minus 1, we can just add x minus 1b, and plus for b equal to xa upon x minus 1 plus 1 till n, we can add xa. So we get this relation, and this relation can be solved. Let's just denote this value as some t, actually k. So this summation would be nothing but x minus 1 into 1 plus 2 plus 3 till k, and then this summation would be nothing but xa plus xa n minus k times. So this is nothing but x minus 1 into k plus 1 upon 2, and this is nothing but xa into n minus k. So we have reduced our summation to this for all the cycles. C a equal to 1 till n, x minus 1 into k plus 1 upon 2 plus xa into n minus k. We have now got this function, but again this is O of n, and this is also, there can be n different cycles, so overall this would be still n square to solve directly. So what we can do is we can use a very clever trick. So basically cycles can only have sizes 1, 2 till n, and this function depends only on the size of cycle. Depends only on size of cycle. So what we can do is, for all the sizes, we can compute this a equal to 1 till n into x minus 1 k plus 1 upon 2 plus x a n minus k. We can compute this for all the sizes, and then we can multiply by number of cycles of that size. And we will perform this summation for all size equal to 1 till n. Now this might look like again n square, since size can be from 1 to n and a can be from 1 to n, so n square. But there can only be a maximum of square root n different sizes. How? Let's just to maximize the number of different sizes, let's assume there is one for size and count. So there is one cycle of size 1, and there is one cycle of size 2, and there is one cycle of size 3. Basically I have minimized the number of cycles of each size so that I can maximize the number of different sizes, and I am using the smallest possible sizes always. So let's just say they are like this, so till x and 1. So basically sum of size of all cycles should be equal to n, right? So 1 plus 2 plus 3 till x should be equal to n, and this is x into x plus 1 upon 2 equal to n. So x into x plus 1 equal to 2n. So x would be in the order of square root n. X cannot be more than that, and this was when we were trying to maximize the number of different sizes. We chose all the small sizes, and for each size we just gave a single cycle. So basically this is the maximum number of different sizes that we can have in a permutation, and the maximum number of sizes would not exceed the order of square root n. So basically this loop would only run square root n times, and this is O of n. So overall time complexity would be O of n square root n. Did you guys understand that solution? I'll show you guys the code. First tell me just if you understood or not. It was a very good problem. I thought almost the same approach, but didn't think that there are going to be multiple cycles of misplaced elements. Yep. There will be multiple cycles. So did you guys understand, or you guys have some doubts? Okay, so I'll show you guys the code for this. Sorry. So this is, I have inputted the vector in one based. Then correct is, I don't think I used it. Okay, so correct is not useful, just ignore that, and cycle is also not. So length is basically length of I would keep the track of how many cycles are there of I size. And now I'll show you how I have computed the different cycles. Basically, I have maintained a viz array. This is you guys can do this using a DFS as well. Basically, pick any unvisited node and start a DFS from there, and the number of different DFS would be the number of different cycles, and the number of elements in each DFS would be the number of elements in each cycle. So I didn't use DFS because it could have been done without it. So what I've done is I've created a visited array and initially marked all elements as 0. And then if the current element is visited, then I just continued. And then if it is not visited, but if vi is equal to I, then basically our count is the number of elements in the current cycle. So if vi is I, then the current cycle is of length 1. If vi is not I, then what I'll do is I'll store the current number with current number as start, and what I can do is while not viz of start, I'll just count plus plus and viz of start as 1. I'll just explain this loop. I'll try run this loop in the test case. Let's just take that test case 1376245. 1376245. So what will happen? And there is a visited array which is initially 0 0 0 0 0 0 0. Okay. So I'll come to this element. Since it is not visited, then I see that vi is equal to I. So this is a self loop. So I'll know that there is a length count. So I know that there is a one length cycle. Then I'll move forward in the loop. I'll go to this element. I'll mark this as visited. Then I'll go to this element. I'll see that it is unvisited. And vi is not equal to I, so this must be part of some big cycle, right? So what I'll do is I'll mark this as visited, and then I'll go to the third index. I see that this is also not visited. I'll mark this as visited. Then I'll go to the 7th index. I see that this is also not visited. I mark this as visited. Then I go to 5th index. I see that this is also not visited. I mark this as visited. And then I go to again 7, which I find that, then I go to 3, which I found that is already visited. So I'll stop the loop, and the number of nodes that I marked visited is the count of the number of nodes in the cycle. So 1 2 3 and 4. So I know that there is a cycle of length 4. Then I move forward in the loop. 7 is already visited, so I just continue. Then I move forward to 6. 6 was not visited, and vi is not equal to I, so I'll mark this as visited and go to 4. Again I see that this is not visited. I mark this as visited and then come back to 6. I see that this is visited, so I stop the loop, and since I marked 2 elements visited, so I know that there is a cycle of length 2. So this way we can find all the different cycles, and this is what I'm doing in this for loop. And then what I'll do is I'll iterate over all the different lengths of the cycle. I ignored the length 1 cycle because that would just be 0 answer, because they don't need any operation. So I started from length 2, and if the number of cycles for this length is 0, then I just continue, and I simply then apply this formula, this one. So B max is len into A upon len minus 1, which was K, len into A upon len minus 1. K is B max and X is len of the current cycle. And B max, if B max is going above N, then I can just limit B max to N, and then I can apply this formula, X minus 1, which is len minus 1, K into K plus 1 upon 2, K into K plus 1 upon 2, and into CT. Into CT we have to do where did we get that? Yeah, into number of cycles, and then the next part x into a into n minus k. So x is len into a into n minus b max into count, and then see out answer. So that was the code for problem B. Many people did DSU. Yes, you can do DSU. You can do DSU. DSU also is can be used to find the number of find all the different connected components, which is basically the cycles in this case. So yes, you can apply DSU for that as well. So I think this question is clear. Let's move on to the next question. So delete maximum. So you are given an array A of n distinct elements satisfying 1 AI till n. Consider performing the following operations as many times as you want on A. Choose a continuous subarray of size A minus 1 and then delete the maximum element of the subarray from the original array. And note that the maximum element is unique due to the elements being distinct, and this decreases the size of A by 1 in each operation. Find the number of arrays that can be formed using the above process modulo this. And n is given as 2e5, and sum of n over all test cases does not exceed 2e5, so expected time complexity would be around O of n. So problem F. So basically we are given an array A where AI is from 1 till n and all elements are distinct. And you can perform two types of operations. Operation 1 is basically you can perform only one operation. Select a subarray of A minus 1 elements and delete the maximum. Now we need to count the number of different possible arrays that we can generate. So basically, first of all, subarray of size A minus 1 is a long subarray. Basically, there can only be two of these. Let's say my A is like this. So subarray of size A minus 1 would be either this or either this. Just two of these. We can either leave the first element or we can either leave the last element. So yes. Now let's see the test cases. So let's see 3142. A is 3142. Yep. So we can perform basically either this operation or this operation, but both of these operations would be giving 4 as the maximum number. So it doesn't matter which operation we perform, we would still end up with this array. So basically the observation that we can make using this is, if the maximum element is in range A2 till AN minus 1, then there can be only one possible array with this as its maximum. Basically, if the maximum element is somewhere in between, which will be removed with both of the operations, with either of the operations, then we cannot do any observation that will preserve the maximum. So it would be removed after one operation. So so basically there can only be this one particular array 3142 where 4 is the maximum, because 4 would be removed after this one any operation. So doesn't matter which we perform, we will get this 312. Now our current maximum is 3. So now the interesting thing some interesting thing happened. Basically we can either perform this or this, right? So performing this would remove the 3 as the maximum of the array. So what we can do is we'll perform this. So when we perform this, we get the array 3 1, and again we perform this. So when we perform this, we get the array 3. So basically, if the maximum is either of the corner elements, then we can perform. Then we can remove all the elements towards the right side of it, and every time we would get a distinct array with its maximum as 3. So another observation, if the maximum element is in corner, then we get let the maximum element be x, then we get x different arrays with x as the maximum. Basically why? Because if this is x and it is the maximum of the whole array, then here we would have the elements from 1 2 3 till x minus 1, and we would remove 1 in each operation, and still the x would be the maximum of the array. So there would be x different arrays with x as the maximum. So there, in this case, there are 3 different arrays with 3 as the maximum, and there was one distinct array with 4 as its maximum. Now let's move on for other cases. Let's say that we performed this operation and removed 3. So we would get 1 comma 2 as the array. Here again 2 is the maximum. So we would get again 2 different arrays where 2 is the maximum, because I can perform this operation and then I will get this. So this and this are 2 different arrays, and then if I had performed this operation, I would get this array, and then I would have 1 different array with 1 as its maximum. So basically the answer for this 5 6 7 would be the answer for this test case. So basically solving this test case gave us the intuition that we need to count the number of distinct arrays with x as its maximum. And then sum for all the x would be the answer. So basically we are trying to calculate this function where f of x is number of arrays, number of distinct arrays, basically this. F of x is this, number of distinct arrays with x as its maximum. This is our f of x. So this would also be equal to the answer, because for each x being the maximum in the array, we are counting all the distinct arrays possible, and we are then summing for all the x's. So this would also be the answer. So let's let's try to calculate f of x. So basically for f of x, we first need to remove all elements greater than x. So basically, obviously, if we have this array, then we are allowed to perform either this or this operation, right? So if there is an element which is greater than x, so it must be in either this or this, right? Because these two arrays cover all the elements. So we can perform the operations and remove all the elements which are greater than x. So then after we perform the operations, we would have three different scenarios. We could have gotten an array like this, or we could have gotten an array like this, or we could have gotten an array like this. So basically, now what happens if we had gotten an array like this, so there would only be one unique array where x is the maximum, because before this x was not the maximum since we were removing the elements greater than x, and after this, no matter what operation we perform, x would be removed from the array. So there can only be just this array where x is the maximum. But for these two cases, here the elements, all the elements from 1, 2, 3 till x minus 1 will come, and here all the elements from 1, 2, 3 till x minus 1 will come. So what this means is, I can perform x operations like this and still x would remain as the maximum of my array. So in this case, the answer would be x. So now if we can somehow check for each x, if f of x is 1 or x, if we know that for each x in O of 1, then we would have solved the problem, right? Now the problem boils down to just knowing if it is x or not, because if it is x, then we know it is x, and if it is not x, then we know it's 1, because there are no other cases. So let's just try and find if the current element can be will be at the corner after I remove all the elements greater than it. So for an element to be at the corner after I remove all the elements greater than it, in the original array, it must be like this, that if x was at some position this, all these elements must be greater than x, or all these elements must be greater than x. So basically, in other words, x must be greater than minimum of this, or x must be greater than minimum of this. And what I can do is I can make a prefix min array and a suffix min array with basically the logic of p of let's just denote this with variable L of I as minimum of L of I minus 1 comma vi ai, and this being r of I is equal to minimum of r of I plus 1 comma ai. Basically r of I is I plus 1 for the answer till I plus 1, the minimum answer, that and the minimum of ai, and similarly the answer till I minus 1, that and the minimum of ai. So these two logics can be used to make the prefix min array and suffix min array, and then we can simply check if ai is greater than li minus 1 or ai is greater than ri minus 1, then basically value of f of x is equal to x, else f of x is equal to 1. So basically L and R can be pre-calculated, and then I can know that the value of f of x is 1 or x in O of 1. So overall time complexity would be O of n, and I'll show you guys the code. So basically, I take the input v, and then I define L and R. So L of 0 is v of 0, R of n minus 1 is v of n minus 1, and Li is basically minimum of Li minus 1 and Vi. Ri is minimum of Ri plus 1 and Vi, and then I'll calculate the answer. For answer, for I equal to 0 till n, for each element I am checking if it is the if it will be the corner element when it is the maximum or not. So for I equal to 0 and I equal to n minus 1, it would obviously be the corner element because there are no elements to the right and left side of it. So for these cases, I add Vi to the answer. Else, I check basically if Vi is less than Li minus 1 or if Vi is less than Ri plus 1. Then I add Vi to the answer. Else, I just increase answer by 1. So, basically, this Vi is less than and AI is less than R minus 1 and Li minus 1. Basically, uh, less than, sorry. Since these must be greater than x, right? These all must be greater than x. Then the minimum value of those minimum out of these should also be greater than x. If the minimum out of these is greater than x, then all of these would be greater than x. And similarly, if minimum out of these is greater than x, then all of these would be greater than x. So we need to check if minimum is greater than x. So that was the code, and that was the solution for this problem. If you guys have any doubts, you can ask. So I think it's clear for you guys. So I'll be discussing only these problems. Thank you.